show you some of the notation that's, the notation with this and some of the kind of the order with which you take some certain steps is just pretty critical for us to really say what we mean when we do this direct substitution, right? I'm on page 22, and right above this, right, the last words that we wrote down, when a function is defined and continuous, I want both of those things, then we can just plug the number in, which is really, really nice. And we know how to do that. We're pretty good with the algebra. Have a calculator nearby. If you don't have one in front of you right now, I think it would be a good idea to have your graphing calculator so that we can do this the direct substitution quickly. I just want to kind of walk you through the steps with these 6, just so you can kind of get the hang of it. And if anything calculator-wise comes up that you struggle with, then we can kind of talk that through. And this is actually the homework for today. And so we'll do it right now, and then you can just submit it, and then you'll be done for this weekend, and then we'll figure out what Monday looks like. I'm having Miss Bates, one of the IT people, come in to try to help me figure out how to do this in the best way so that your experience in class is great and your experience at home is just as good as it has been. So if you have any thoughts as to what's been working with you being remote, and what hasn't with kind of calculus so far, I'd love to hear that so I can make adjustments. So the good and the bad, I would love to hear that, whatever that is. So if you have ideas on that, please feel free to share that with me. I take constructive criticism really well. So don't hold back. If you've got great ideas about how I can get better, please let me know. Okay, so let's do this. The first big thing about evaluating limits directly with what's called direct substitution comes in to an issue that I have with the notation that's here on only one of these problems. It just happens to be the first one. Take a look at that first one. They want the limit as x approaches 3 of this function. The problem that I have with A compared to all the other ones is that A is the only one that has more than one term, right? You've got, one fraction, you've got one fraction, you've got one trig expression, you've got one trig expression, you've got one logarithm. And there's nothing being added or subtracted to that. And the thing that we have to realize is when we say things like the limit of blah, 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 right? It's kind of that function kind of connection, right? Where we don't necessarily need parentheses to say the word of, but that's kind of what we mean, right? F of x, we always put the parentheses around x. And so for me, and I think this is true kind of across the board. I'm not sure why they're not there, but the way that I would read A, if it's written like this without parentheses around that polynomial, is like they just want the limit of the 1/2 x squared. And then everything else is just negative 2x plus 3, like has nothing to do with the limit because the limit is just connected to what's right next to it. And so for me, and maybe I'm just like pickier than normal when it comes to this, like if you want me to take the limit of something, I need to know like everything that you want me to take the limit of. And I need to know where that begins and ends. And if there's only one term, like b through f, then I know that you want the limit of what's right next to it. But I think we should be adding in some parentheses right there around all of that polynomial so that we know to find the limit of the whole thing. Maybe that's overkill. Maybe I'm doing more than I need to. But I think that when you have more than one term and you want the limit of all of it, that you should tell me you want all of it. Because we're going to get to the point where we're going to take limits of this piece, but not the limit of this over here, because that doesn't have to do with the limits, right? And so I think it's just a little bit better for us to put parentheses around things that just have more than one term. Okay, so that was kind of the big thing that stood out for me in this one. The other thing that I want us to realize is that when we evaluate these limits, and we've been doing this the whole time, we always want to kind of connect things with equal signs as we go, okay? So like the first thing I'm going to do after every limit is I'm always going to kind of start off with a nice equal sign after each one, because we're just going to connect equivalent expressions, okay? And you'll see that like along the way here next week, like we're going to have to do some like, like reorganizing and some algebraic manipulation to make things look the way that we want before we can actually plug stuff in. And so what you'll see kind of moving forward is that like maybe I can't take the limit right away. Right? Maybe I'm approaching a hole, or maybe I'm approaching an asymptote. And if I just plug in my number right now, like I'll be dividing by 0, and that's no good. And so we might have like the limit, blah, 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 equals the limit, blah, 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 blah. And we'll just kind of change the equation around. And equals limit, equals limit, equals limit. And finally, we'll get to a point where we can actually plug the number in. Well, what I want to be able to do, if I can, is go right to plugging the number in, right? Go through direct substitution right away if I can. And of course, the only thing I'm really worried about is dividing by 0, right? Taking the square roots of negatives, stuff like that. All of the things that we know we can't do in the real number system. And we're not dealing with anything imaginary for a very long time in calculus. We like real numbers. And so, like, look at A. Like, is there any problem you see with plugging in 3? Like, do you think we're going to run into a hole, or do you think we're going to run into an asymptote in just a nice little, like, it's just quadratic. There's no gaps, there's no holes, right? I can plug in that number right away. And so here's what I want you to realize. The moment the number actually goes in, right? The moment that x disappears and becomes, in this case, 3, that exact portion of our work is when the limit notation can disappear. And what I mean by that is, like, direct substitution we love because what we know about functions that are defined and continuous is that the value of the limit and the value of the function are just going to be the same. But I don't want to hold on to that limit as x approaches 3, limit as x approaches 3, limit as x approaches 3, if I'm already plugging in 3. It's like changing f of x to f of 3. Like, I don't hold on to f of x the whole way. Like, I want to actually plug in a number and see what happens. And the moment I do that, the f of x changes and becomes f of 3, right? And so here with this whole limit notation, okay, like they're saying, okay, go to 3, see what's happening. And in the back of our minds, we're saying, well, is there really anything holding me back to just going to 3 and seeing what's happening at that point? Do I feel good about it being defined and continuous? And if the answer to that is yes, then, like, in my next expression that I'm about to write on the other side of this equal sign, the limit notation is gone once the 3 goes in, or once the 3 goes in, or once the 2 goes in, or once the pi over 2 goes in. When you substitute, drop the limit notation. Are we cool with that? Do you kind of understand why? Okay. So when I say, okay, hey, let's find the limit as x approaches 3 for this quadratic. Well, okay, it's defined. It's continuous. Why? Because it's a polynomial, so I know I'm good. Then let's drop the limit as x approaches 3 part and actually change x to 3. And I want to see that transition. Okay, so I want to see this, 1/2 parentheses 3 squared minus 2 parentheses 3 plus 3. Okay, the limit is gone. And instead, the x value goes in. Okay, so that kind of crucial change to the notation is really why I wanted you here today, so that we could talk about, 1, I think it's important we put parentheses around polynomials. And 2, as soon as your number goes in, the limit goes away. Okay, and we're going to hold on to that, that thought process all the way through calculus. Okay, now, do not do this part by hand. Type that in the calculator and see what you get. Okay, so I want to see 2 steps. I want to see the direct substitution, and then I just want the answer. Now, if you want to do steps in between, great. Of course, you can always show more work. You just can't show any less than these 2 steps. Okay, show me the direct substitution, and then let the calculator do the evaluating, as long as your answer that you get at the end is perfect, right? If you have a nice, perfect exact answer, whether it's a fraction, a decimal, something irrational, whatever it is, write that perfect answer down. So what, 4.5, negative 1.5, 1.5, or 3/2? Cool, done. Those are the two steps that I want to see. I want to see the number go in as the limit disappears, and then just simplify, okay? You can do that from the red to the blue in as many steps as you want. But what I've got looks great, okay? And so when I kind of slide over here to the second one, like I felt really good about A because it was just a polynomial. I know polynomials are continuous. I don't have any worries. Well, now my heart kind of slows down for a second, and it's like, okay, well, hold on, wait a minute. This is rational. We know that tricky things can happen when we divide by 0. And we just want to make sure that we're not doing it. And so before I actually drop in the number, like really, like actually show that step, I think about what would happen if 3 was going to go in. And I only really care about the denominator being 0. Because if it's 0, I gotta do something different because I can't just plug it in. But if it's not going to be 0, then I feel really good about dropping that number in and not getting something weird back, right? The only thing about rational functions that's tricky is that, right, dividing by 0. And so I look at B and I say, okay, you want me to go to 3? I just have to make sure that there's no asymptote or hole at 3, making sure I'm not dividing by 0. And so look at the denominator. I don't care about the top. The top can be whatever we want. I just look at the bottom. And I say, okay, imagine dropping in 3. Okay, so 2x minus 3 becomes 6 minus 3, which is just 3. Cool. That doesn't bother me. I don't mind that. So I feel really good kind of ahead of time thinking about what's going to happen if I drop that number in. Kind of focusing on the only part that I'm worried about. But now that I feel okay, knowing that the denominator will be 3, here's where I drop the limit notation and I show the step of substitution. That wherever there was an x is now 3. And again, between the red and the blue, you can show as much arithmetic as you want. Okay, but if you have a good graphing calculator that you can type things in correctly, just make sure like you put your numerator in its own set of parentheses. Like it would have to be like that and like that if you want the calculator to do the correct work for you. You can type that all in at once and see what you get. Now what's going to happen in this case is you are going to end up with a repeating decimal. And we can't use that, of course. So if you are in your graphing calculator and you are typing that in just like that, right, you're gonna get, what, 5.66666666 forever, right? Change that back to a fraction, okay? Go to math, option number 1, right, arrow frac, change it back to a fraction, press enter twice, one to put it into the screen and then one for it to actually do that, and it will give you that 17/3, and that's the answer that we're looking for, okay? Now, of course, you could just do that, right? 5 times 3 plus 2, 17. 2 times 3 minus 3, 3. And you're going to get to 17/3 mentally without having to rely on the calculator. So whatever path you want to take, you can use a tool or not, totally up to you. Okay, all right. So if you're okay with that kind of thought process, that's all I really want to do with these direct substitutions is pause for a second, think about the restrictions on my domain for the kind of functions we've looked at. If there's nothing holding me back, I'm okay with plugging it in. If I'm worried about dividing by 0, square rooting negatives, I just think about plugging it in first before I actually go through that process of dropping the limit and changing the number. So when I get to C, okay, you want me to approach 2 from the left, right? That from a little minus, yeah. Well, with direct substitution from the left, from the right, it doesn't matter. They're all going to be okay as long as it's defined and continuous. And so I look at a rational function and I say, all right, I just want to make sure whatever I plug in doesn't make me divide by 0. Okay, plugging in 2, I'll be dividing by 3. No big deal. I also have a square root on top, so I want to kind of be careful there too to make sure I'm not getting a negative. Okay, plug in 2 under that square root. Yeah, 2 plus 2 is 4. Again, I feel okay. And so what I'll do is I'll just go for it, right? I will drop the limit and I will change x to be whatever that number is that they want me to plug in, whatever that limit is that they want me to look at. And as much work as you want to do between the red and the blue, that is totally up to you. Okay, you can plug it all in all at once, just making sure that you have those parentheses around the top and around the bottom if you are going to do zero mental math. Great, go for it. Okay, because if that's what happens, you should get to the point where you get a rational answer, fingers crossed. If you get something irrational, oh God, okay, I got to back up and I got to do some arithmetic myself because my answer is like the square root of 5. The calculator is going to spit out some decimal that's going to have no pattern in it, and I can't change that back to something rational, right? Unless you have irrational, unless you have I think it's an 89 or a titanium, or even the TI Inspire, I think it can give you irrational simplified results, which is really nice. But for us, this one's rational, right? Because it's square root of 4, so 2 minus 1 is 1, 1, 1, 3. But you would have gotten 0.333333 if you typed it in correctly, and so I got to change it back to a fraction. Okay, all right. With this one, it's just sine of 2 theta, like the parentheses. You don't have to write them, but they are there. That before I actually evaluate sine, I just have to do 2 times that. Okay, but sine, domain is infinite. So I feel really good about plugging a number in and seeing what I get. So I'm going to do sine of 2 times pi over 2. And that's what that means. And I don't evaluate sine of pi over 2 yet. I have to multiply it by 2 before I can actually evaluate, right? Because parentheses before we do anything else. And so maybe you write a step like this. Okay, that's really the sine of pi. All right, because 2 theta, and theta was pi over 2. And if you're in radians, a calculator can help you out as long as it's quadrantal, and it is, which is really nice. Or maybe you know the unit circle really well, or maybe you have the unit circle out nearby, but that's 0. But again, that step in blue is up to you. If you want to write that sine of pi step, go for it. But you can type in sine of 2 times pi over 2, and it's going to give you 0 either way. Okay. Last 2 really quick, and then we'll be done. Thank you guys for being here. I just wanted to walk through these with you. We will get a chance, certainly before we do anything for real, like a quiz or test, we'll definitely practice these ideas. This one's a little bit trickier because it's cosine of theta over theta. It's a rational function. So if it was just cosine, I wouldn't worry about it. But because it's rational, right, I want to make sure I'm not dividing by 0. Well, theta is going to 2 pi over 3. So my denominator is just going to be 2 pi over 3. So I don't really feel too worried about plugging this in. But I know I'm going to have some simplifying that's going to have to happen here. So again, drop the limit, right? My first step with direct substitution, drop the limit, plug in the number. So cosine of 2 pi over 3 over 2 pi over 3. Now I'm going to give myself some space to work here because simplifying that, a calculator might be able to work with it a little bit, but I've got pi as part of my answer, which means my answer is going to be irrational, and so I don't want to round. Right? Unless they ask me to, I really don't want to. So I kind of have to take some steps here, which is why I'm going to include these in red because I think that they're required at this point. So I have to go to 2 pi over 3 and see what's happening at cosine. Luckily, that one's not too bad, right? That should be just negative 1/2 over 2 pi over 3. Right, 2 pi over 3, yeah. Okay. Yikes, gross. Complex fractions, right? One fraction buried inside another fraction. Really, it's actually 2, right? You got a fraction on top and a fraction on bottom. So I think the easiest way, I'm just going to change color so you can see the difference, but I still think this is pretty crucial for us to be able to find the right answer. To make it a little bit easier, instead of taking a fraction and dividing by another fraction, let's take that top fraction and multiply it by the reciprocal of the other one. Okay, that is going to be your best and easiest path of least resistance when it comes to dealing with complex fractions, right? Just take the top one, leave it the same, and then multiply it by the reciprocal, which we know we can do. And then simplify if you can, right? If there were common factors, top and bottom, away they go, right? If you had a 2 on top and a 2 on bottom, or a 4 on top and a 2 on bottom, like take any kind of simplification steps that you can, but nothing really, right? Because you have 1 over 2 and 3 over 2 and 1 over 2 pi and 3 over 2 pi. There's really nothing that goes together. So we can just multiply straight across. That's how we're going to simplify fractions straight across. A negative times a positive is going to be a negative number. So I put a negative in front of a fraction. 1 times 3 is 3. 2 times 2 pi is 4 pi. Okay, and that's really the one I wanted to make sure that we got to, so that we can see how that can be a little tricky, right? You had to know your unit circle a little bit. You had to know what to do with these fractions. You had to know that it's okay to plug in that number from the beginning. Okay. All right, let's do one more, and then I'll get you out of here. So one single term here, right? Log base 8 of 11 minus x. Logarithms are not all real numbers for their domains. I know we didn't look too much at graphs of logarithms, but they have, just like exponential functions have horizontal asymptotes, right? We talked about that yesterday. Because logs are the inverse of exponentials, that horizontal asymptote becomes a vertical one. And so you have graphs that kind of look like this, where eventually, that's a vertical asymptote, eventually there's going to be some x values that we just can't plug in at all, because they would make the argument negative. Okay, what's inside the parentheses in a logarithm must be non-negative if we want to get an answer back. But imagine plugging in 9, right? Think about it first. Oh, well, 11 minus 9 is 2. That's non-negative. I feel good about it. Let's go for it. Let's drop the limit, and let's change our x value to whatever they want. Okay. Again, show the work here if you want, or be comfortable with figuring out how to type that in your calculator. If you've got an older calculator, there is no log base 8 button or function in your calculator. If you have a newer one, it's in there. I think it's math, and you have to kind of scroll down to I think it's option A, which is log base. So that you can type in log, so you press like the log base button. It will have 2 empty spaces, one for the base, which will be 8. And then you write arrow, which will take you into the argument, which is the stuff inside the parentheses. And you can just type 11 minus 9, or you can type 2. All right, so here's kind of the step in between. This is log base 8 of 2, which is asking the question, 8 to what power is 2? That's what a logarithm is. The answer to a log is an exponent. 8 to what power is 2? Well, the cube root of 8 is 2, so that would be 1/3. Not a thirds today. There you go. Done. Homework 1.2. Once you're good with that, take a photo and upload that to Canvas for your work for today, and you are good to go. Questions, though, about anything that we talked about? We okay? I know it's kind of early on with direct substitution, so we'll definitely keep working through it. What you'll see as we turn the page to page 23 is that we just can't plug in the number yet. We will eventually. We'll just have to do a little, dividing stuff away that's causing problems, like thinking back to rationals and like how we found the whole in a rational function. All that stuff's going to come back. So we'll be able to kind of work on that. So I just wanted to kind of talk through some of those ideas with you. So thank you for coming, hanging out with me today. I went a little bit longer than I wanted to, 25 minutes, but not too bad. So I will kind of put out a plan for Monday. what cohort A will be doing, and then we'll just be coming into class, yay. And then what cohort B, you guys will live stream in. I just have to figure out how I want the room to get organized, and maybe what added technology I need to kind of make it work, so that this setup with me having like chairs on top of desks maybe isn't quite so much in your way to be able to view the projector, because this is definitely the easiest way for me to work through these guided notes, is to project them up here and then right on top. So we'll do our best. We'll be flexible. We'll make it work. So y'all good to go? I will see you in one way or another on Monday. Yay. Have a good weekend.
Mr. Rosengren, I have a quick
question. What's up? Sure, please.